Okay, so on Friday, we started looking at differential equations, and hello, welcome. Welcome back. Have you had your lab test?
I did, yeah.
I hope it went well. This is mostly Math 1, 2, 3, 1. Okay? So you'll get a few flashbacks from that. And an ODE has two things in it. Yep. It's got an equal sign because it's an equation, and it's got derivatives. Okay? And like any kind of equation, we would like to solve it. We would like to solve it. Okay? And in this case, the thing that we're looking for is a function. A function, not a number. Right? We're not solving a quadratic equation, right? But we're looking for a function, okay, that satisfies the derivative, or the differential equation. Okay, so I showed you one example on Friday, and it was called a separable differential equation. And I think they're probably the entry level for like a first lecture in differential equations, okay? So we use the word separable because it's sort of got to do with the method of solution, right? It basically means you can use multiplication or division to separate the variables, and then you integrate, okay? So you can see here I can multiply both sides by y, both sides by dx, and I get something like that. And then I just integrate. Okay? Now, sometimes it's an easy process. Sometimes it's a little bit of fiddling around with constants and initial values and stuff like that. In this question, we're told y of 0 equals 1. And we can use that to sort of understand a little bit more about which parts are relevant and which parts are not. Okay, so I actually think separable differential equations are the most accessible, and they're sort of the entry-level starting point. Now, the main idea here, the reason why it works, is actually the chain rule for differentiation. Okay, that's if you wanted to sort of more formally understand why you can pull these things apart and integrate, it's actually the chain rule at work under the hood. Okay? All right. So that was our entry level stuff. Yep. And then we did another one over here. Okay? All right. So today we're going to keep with the first order vibe, and we're going to look at so-called linear first order. See, this is still not working, even though they closed my ticket. Hey, they wrote to me and said, "Oh, we've closed your ticket." It's still not working, UNSW. Hello. Yeah, I'm looking at you, right? So you will, again, have seen this in Math 1, 2, 3, 1. Math 1, 2, or 1, 2, 4, 1, right? And what is this, the basic calculus thing at work here? It's the product rule. Okay? So for separable equations, you've got a chain rule that's going on under the hood, making things work, right? For these linear equations, you've got the product rule. And I'll show you how the product rule works, but we remember it from like high school math, right? Okay, so this is your general form of a so-called linear first order differential equation. So what does the first order mean? Can anybody tell me?
It's been derived once.
So the highest derivative in the equation is just the first order, right? Okay. What about linear? what does this word even mean? Okay, so if you look at this general form, there's only the first order derivative and nothing else, right? And we're looking for the solution y. What does linear mean? We sort of think about maybe straight lines, stuff like that, right? In this context, it's a little bit different, okay? In this context, it's a little bit different. Essentially, it means that if you have two solutions to the problem, then the sum of those two solutions is also a solution. Okay, you can talk about linear operators, stuff like that. Maybe you're getting a few flashbacks to 1, 2, 3, 1 algebra there. But that's okay, it's not necessary to know. All right, this is the most important thing that I've said so far. Okay, all right. So what does a linear differential equation look like? So might look like this. Sorry. Doesn't look like that. Okay, plus, I don't know, 2xy equals 6x squared. Okay, so this is an example of the general form. So in this specific one, p of x would be 2x, q of x would be 6x squared, and we're looking for some function whose derivative plus 2x times its derivative gives you 6x squared. Okay? All right. Now, don't tell anyone this, but sometimes there's a super easy way of solving these problems. Okay? A super, super easy way. And I try to use it all the time when I can. Okay? And yes, it's based on, let me see if I can do this. Yep. The product rule. Okay? But in some cases, you just need to move things around a bit. Okay? So let me show you what I mean. Let's have a look at this problem. So in this case, p of x is 1 on x, q of x is x squared. All right? So what happens if I move the x and multiply both sides by x? Yep, it's the same. Let's get that aircon back on. It's the same equation. I've just multiplied both sides by x, right? Now, what do you notice about that and the product rule? Remember, y is a function of x here, yeah? Can anyone see it? What is the connection between the left-hand side and the product rule? Anyone at home? Hello? Oh. Okay, it involves, yeah, okay, so I'm missing the afternoon. Sorry, I'm missing the messages. Oh. Okay, I'll come back to some of these questions. They're good questions. Okay. Online, someone's saying it is the product rule on the left-hand side. Well, how is that the product? Well, let's have a look at this. If I have the product of x times y, where we don't know what y is, it's just a function of x, and I differentiate that product, what do I get? Well, it'll be x times dy dx plus 1 times y. Okay, so it's the same. It's the same. Okay, product rule. So how can we use that to solve this kind of problem? Well, I'm glad you asked. So this goes to that, and now we've got the derivative of something equals a function of x. So what can I do? I can integrate, get rid of the d dx by integrating with respect to x. Okay? So I've got these things trapped in this derivative. if I integrate, that'll come undone, and I'll get something like a quarter x to the fourth here. Plus a constant. So I'm chasing the y, so what I can do now is just divide both sides by x, and I get y equals something. Okay? So divide by x, and I get a general solution. Bump, bump, bump. Okay? So the most important realization there was knowing that the left-hand side could be written as the derivative of a product. And then you know what to do with derivatives? Integrate them, right? Integrate them. Okay? Okay, so let's get that constant of integration now. How do we do that? Well, we're going to use part B. So we're going to find that C in there by this by introducing this data. Okay? All right. So let's go in here and sub in x equals, x equals 0. Make sure I write it down correctly. Okay? X equals 1, and we set this whole thing to 0. Okay, so C is going to be -1/4. Okay, so we just replace C with -1/4 in there, and we have our full solution. Okay? So we can check that if we want to by differentiating it and putting it into our original equation, see if it balances, and checking the initial condition. All right? Questions? The main idea is the product rule, okay? We saw the chain rule on Friday, that's why it works. The product rule is why this solution method works.
It might be kind of dumb, but wait, how do you like get the XY? Like I know that the whole logic and everything, but like for like different like questions, yeah.
This is the easiest problem, right? It won't always be as easy as this with the product rule, but you can force it to become the product through a thing called an integrating factor, okay? An integrating factor. So this is, all we had to do in this one was move stuff around and we got the derivative of a product straight away, right? It's not always that easy. It's not always that easy, okay? So we have this thing called the integrating factor, yeah? Which is defined as this. So just let me write out the equation again. Just work. Okay, so the integrating factor, it's defined in the following way. It's the exponential of the integral of that. Now, if you take that and you multiply through your original equation, the left-hand side will be the derivative of this product here. Y times this crazy integrating factor. Okay? So you reduce it to the derivative of a product, and then you integrate and rearrange. Okay? So let's do an example where it's not so easy. Okay? Let's do an example where it's not so easy. So what have I got here? I'll do this one. Okay? I'll do part B. So, what are we looking for? In part B, we're looking for a function y such that its derivative plus 2x times the function adds up to give you 2x. Okay, now we'll look at applications of these later, but we're just solving them at the moment. Okay? So if you think about this one, it's not as nice. The left-hand side is not as nice as the previous example, because you can't just, at least I can't just visualize what it's going to look like as the derivative of a product. Okay? So let's follow the step-by-step advice in here and form what's called an integrating factor. Okay? And then you'll see how it sort of drops out super nicely. Okay, so it's e to the integral of 2x dx. So that's my p, that's my q in this case. All right? So if I integrate e to the 2x, the integral of 2x, I'll just get e to the x squared. Now, in these problems, there's no need to put a constant of integration in. Pretty much everybody asks me, oh, where's the constant of integration? If you feel strongly about it, you can put a constant of integration there if you want to. You're not going to be wrong. Okay? You're not going to be wrong. All right? So, we didn't have to do this in the previous question, but let's multiply both sides of the original equation by this integrating factor u. Okay, so e to the x squared times the y dx plus 2x e to the x squared times y equals 2x e to, so I'm a little confused now. It looks like we've made this more difficult. We've made it more difficult, haven't we? No. Right? No. Check it out. The left-hand side is just the derivative of this product. Wow. Okay? So, you've come just at the right time. It's good. How'd your lab test? Lab test? Tomorrow? Tomorrow. Good luck. Okay? So, what I'm trying to say here is that we've forced that equation through multiplication to have a left-hand side that is the derivative of a product. Okay? The derivative of a product. So that is the derivative of this special product. Okay? You can expand the bottom line if you want to, and you'll get the left-hand side of the previous line. Okay? But now we're in the zone where we were in the previous question, right? We're in this place now. We didn't have to multiply by anything crazy in here. So what do we do here? We're going to integrate both sides. We're going to integrate both sides. Okay? So you integrate both sides, the d dx will disappear. What is the derivative? What is the integral on the right-hand side? What does it simplify to? Who can tell me? Yes. Yeah. e to the x squared. Okay? And now, let's make y the subject. That's what we're searching for. We're searching for this unknown function. Bring that to the other side. Okay, k equals constant. Mit a capital K. All right? Do we know what k is? No. Can we find it? No, because we're not given any extra information. Oh, okay. Oh, I think you could have a C if you wanted to as well. You could have a C if you wanted to. Okay. Extra points if you use a K. Questions? Questions? Like, let me tell you, it's nothing more than the product rule. That's it. Okay, people go, wow, this is mind-blowing. The product rule is amazing. That's all it is, the product rule for derivatives. And you are forcing that left-hand side to be the product of like the derivative of a special product. Okay, so when you go from here to here, you're forcing it to be the derivative of a special product. Okay? That special product involves the integrating factor. And that is determined by P. All right. Let me show people what's happening at home. Chris, I'm wearing AirPods right now. That's okay. You're allowed to if you're at home. Okay. Now, this is controversial. Are we going to get some lab test 1 revision in this lecture? I don't think that's fair, because some people have already sat the test. I would love to, but I can't. What if I passed out during the test and thus wouldn't be able to tell anyone? Well, you wouldn't submit the test then, would you? Right? It's only if you turn up and submit the test on the due date. So I think you'd be okay. Hopefully someone would come and help you. Hopefully someone would come and help. Or maybe people are hyper-focused, right? Like somebody falls asleep or something, you know. Don't be that kind of person. Be a helpful person. All right, questions for this one. Let me ask you, who has a vague memory of this from first year maths? Okay, it's all right if you don't, but it's super helpful. Okay, it's super, super, super helpful, right? Now, super, super, super helpful. All right. Any questions at home? No. All right. So let's just do, I won't do it all, but for part A, what's my integrating factor? It'll be e to the integral of negative 2x. Okay? So then you take that, you multiply your original equation in part A by e to the negative x squared, and then you collapse the left-hand side down to the derivative of product. Now remember, in part A, you've got a little bit of extra information. You've got what's known as an initial condition, and you can use that to get any constants of integration that you calculate. Don't have that in part B. Questions? Okay. All right. Now, for something that you probably haven't seen in first year. Did anybody do Math 1241? The higher? You might have seen this, but I don't know. You tell me. Okay, you tell me. This is something that most of you will not have seen before. Okay? You will not have seen before. But, fear not, the underlying idea here, again, is a product rule. Okay? Gosh, the product rule is so useful. Okay? All right. So let's look at the equation, and then we'll come back and do a little bit of theory. Okay. So here we have dy dx equals this. Okay. The first question, is that a linear differential equation? Is it a linear differential equation? Is it linear? Hello. Welcome back. 50-50. Huh? You're not sure? 50-50. Well, let's have a look. Let's have a look. Okay. Let's have a look. Does this look like that? You just come for 2 seconds and then, where are you going? It's okay. All right, do come back. I liked it how they got up and then they saw that I saw them and they tried to sit back down again. That was good. Just go. Don't worry about me. All right, so, hang on, I need to put that on the screen. It's so funny. It's like, how can we sneak out? All right, so let me move this up a bit. Is that and that sort of the same form? Can you sort of rearrange the top equation to get the bottom equation? If so, what's P and Q? So it sort of looks a bit like this, but we're sort of dividing by a y, so that's a bit weird. We're not doing that here. So I would say that they're different kinds of equations. Yeah? I would say that they're different kinds of equations. And in fact, if we write it like this, so I've just divided on the right-hand side, top and bottom by x. It's a general form called homogeneous first order. Okay? So you can see here this y on x is sort of part of a general form. Okay? So it's not linear. Another question is it separable? Okay? If you're given this equation, can you separate the variables and integrate by multiplication or by division? I don't think I can do it. Maybe you can, but I couldn't find a way. Right? So we don't know what to do with this equation. It's not separable and it's not linear. So what do we do? Well, this is another tool that we can use. Okay? The idea here is the product rule, right? So think about this form here, and there's an example of it in my example. We're going to make a substitution, and then we're going to use the product rule. Okay? So, believe it or not, we're going to take this equation and make it separable. We're going to make it separable. Okay? How do we do that? Well, I'm glad you asked. I'm going to let v equals y on x. So basically, remember, y is the thing we want. It's a function of x. And here I've got y on x throughout my differential equation. Okay? So if I do that and I move the x to the other side, I get this. Now what I'm going to do is set up a differential equation for this v in this v for this v function. Okay, so how do I differentiate this bottom bit? Product rule, right? V's unknown. We don't know what it is, right? If we know what v is, we know what y is, but we don't. So what I'm going to try to do there is form a derivative for y and turn my original problem into something involving dv dx. Okay? So, by the product rule, all right, so let's differentiate this. It's going to be something like x times v dash plus 1 times v. Okay? All right. So now, let's replace that with v, and instead of having dy dx there, I'll put this mess in. All right, so dy dx can get replaced by this mess. It's going to be okay. That's going to be v, that's going to be v. So let's see if we can work that out. Okay. It looks like we've made it worse. But if I rearrange things, I can separate the variables. Okay? So our objective now, we'll get v from this somehow, and we'll use that to get y. So, you know, y is just going to be x times v. All right, that's the idea. Okay, so let's rearrange this. Solve for v. All right, great. So let's rearrange. Okay, I can put that all over one denominator if I want to. Okay, so now we're in business. That equals that. Okay, I've just simplified the algebra. You don't. Yeah, it's better if you do that. So it's separable. It is separable. We can separate the variables and we can integrate. Okay, remember how we separate variables in this course? For separable problems, we either multiply or we divide. We multiply or we divide. Okay, so we can do that here. Okay, we want to get the v's on one side and the dv's on one side and the x's and the dx's on the other side. Okay, so let's separate. Separate the variables. So that the v's will come to this side. Let's go that. And the x and dx's will come to the other side. Okay, so that's going over there, that's going down there, and that's going up there. All right, so on Friday we talked about this. Once you've separated the variables, you integrate both sides. Okay? So now it's just a little game to try to integrate. Actually, you know what? I'll keep the minus sign over there. Okay, doesn't matter where you put the minus sign. Just in my notes, I've just kept it over there. All right. So let's look at this left-hand side. I'm going to write it like this. Okay. So integration time. What is the first integral with respect to v going to be? Yep, so it's going to be something like log of v squared plus 1 and maybe half of it, half times. Yep. What about the second integral? Now remember, you will get a table in the final exam, so you don't have to stress too much about it, right? How do we integrate something like that? Tan inverse? Yeah. What about that one? Log? Yeah. And then a constant, right? So over here, now x is positive, so I don't need to worry about absolute values here. And this is always positive, so I don't need to worry about absolute values there. Holy moly, what a mess. But the important thing is, we've got an expression for v now in terms of, what am I doing? V. That's better, right? Is that what your question was about? Oh, what was your question about?
In the step that's x dv over dx plus v, what's stopping us from just making that into like how we did the integrating factor thing with y? So just dv over dx xv?
So you're talking about this bit?
No, the step before that becomes, yeah.
Yeah, because this is a problem, right? This is a problem because if they were x's, it would be fine. But if you collapse that and it's d dx of something, how are you going to integrate that with respect to x? Because it's v, and you don't know what it is. It's a good question, though. Okay, so it's a mess. But what is our final answer going to be? Remember, all the way up here, we let v equal y on x. So we'll replace v with y on x. And that's the best we can do for a problem like this. Okay, so it's a bit of a mess, and people get angry about it. You can probably bring the logs together if you wanted to, but I'm okay with that form. It's called an implicit solution. You can't really invert that and say y equals this nice thing involving x. Okay, so it sort of shows you how complicated some of the solutions to these problems are. Okay, they're super complicated. Maybe they're not chaotic, but they're still complicated, right? They're still complicated. Welcome. You had your lab test? Yeah. Oh, what were you doing? Did you go out and come back? Oh, it looks like you just sat down, and I'm like, oh, I'm so sorry. How was your lab test? Oh, tomorrow. So you can see that even for a sort of a reasonable looking question, like it doesn't look that bad on the surface, right? It doesn't look that bad. The solutions can still get pretty crazy. Okay? So let's play a little game. Let's play a little game. Ooh, someone's seen homogeneous. All right. So here are the main forms, right? So just give me a second. How did I write that? Yep. Okay, there are our three classes, or our three groups. The first one is separable. Second one is linear. Third one is homogeneous or homogeneous. If you come from the States, I'll go to the States, people talk about homogeneous solutions. Okay? Now, the skill here, part of the skill is to know and classify something that's in front of you. Okay? So, and everyone at home, you can join in too. Right? I want you to smash that chat button. Now, what is this? Okay, is it separable, linear, or homogeneous? Who thinks it's separable? Okay, who thinks it's linear? Who thinks it's homogeneous? It's all three. Wow. It's all three. Okay? But if I do this, if I make a radical change, is it still separable? No. Is it linear? Yes. Yes, it's linear because I can write it like this. Right? That's linear. Is it homogeneous? Yeah. So it's no longer separable, but it's still in two of the classes. Okay? It's still linear and homogeneous. So what? Okay? This means that when you get a problem like this, sometimes you can use different methods. Yeah? Sometimes you can use different methods. If you have a favorite, maybe you have a favorite method, right? You love to separate and integrate. You can do that maybe, right? You can do that. Or if you love an integrating factor, you can do that. Or you love to make a substitution for the homogeneous problem. You can do that too, okay? It's totally up to you. It doesn't always work like that. Let's do another one. Yeah, separable. Okay, good. Keep the questions coming, or the comments coming at home. Okay, what about this one? Yeah. Okay. Who's ready to play? Is it separable? I don't think it is. I don't think it is. I don't think it's separable, right? You can try separating you know, people argue with me on YouTube for like years, right? They go, oh, I just bring the x up there, then take away 2x from both sides, and it's fine. No. When I'm talking about separating and integrating, it's division or multiplication only, okay? Adding, subtracting is no good. But people will argue with me in the comment section for hours, right? I don't know what to do. Okay, so I don't think it's separable. Is it linear? Yes, it is, right? Because I can write it like this. Let's say y on x plus 2, and I can shift that to the other side, and then it's a bit like that, right? So yes, it's linear. Is it homogeneous? Yep. Now, a good question here is, come on, I can't deal with all these methods, just tell me what to do. Tell me what to do. I would choose the easiest method that you're comfortable with, okay? I would choose the easiest method, right? So don't make it complicated if you don't have to, okay? Don't make it complicated if you don't have to. You can if you want. But to me, it's all about solving it quickly and, you know, efficiently and correctly, Okay, let's do another one. Okay. Yes? Hang on. Hang on. This sounds like a good question.
Is it like a case where like all separables can be written as linear and homogeneous, but not all like homogeneous can be written as separables?
Okay. So you can see here, so it's a good question. So does one sort of encompass the others? I think that's what one of the others. So you can see here, that one's separable, linear, but not, that one's linear, homogeneous, but not separable, right? You can have problems that are homogeneous, but not linear. Do you want me to give you an example? Okay, I'll give you an example. Okay, can it be separable but not homogeneous or homogeneous? Okay, let's see if we can find an example. It can be homogeneous and not separable. Can it be separable and not? A non-homogeneous one, okay. What about that? That's not, that's separable but not homogeneous. Right? That's separable but not homogeneous. Would you agree? Yeah. So sometimes they overlap and sometimes they don't. Yeah. But it's good to look for the patterns and the, all the different subsets and all that sort of stuff.
I was just going to ask if it has a y on x term, does that mean that it's homogeneous? Like homogeneous always has has to have a y on x term.
Yeah.
Okay, cool.
Yeah. Exactly. If you can rearrange it so you've only got y's on x's in there, but you've got to be careful, right? So although this one is homogeneous, if I do this, it's no longer homogeneous. It's not. Because that x on the end is just out there on its own. You need a y above it to make the homogeneous form work. Exactly. A constant's fine. But, so yeah. So as you can see, it's like a little game, a little sort of, I don't know, art form or something to classify these things. So, so this is definitely separable because that's fine. Yep. Okay. So the difficult thing isn't really solving it. It's looking at it and saying, it's this or this or this. I'm going to pull this, method out and solve it. That's actually the hardest thing. Okay? For me, that's the hardest thing. Because if you can't classify an equation, what tool are you going to use to solve it? Well, you could use all sorts of stuff, but you're kind of guessing, which is okay, but it's better if you don't guess. Other questions? Other questions? Oh, gosh, I've gone over time. God, I'm getting so into it. Sorry for everyone. Let's take a 10-minute break and we'll come back in 10 minutes or so. So, this is the bigger picture for these homogeneous problems. Okay? So essentially, if you recognize that it's of a certain form, you make a substitution, and it spits out a separable differential equation in this U or this V or whatever you want to call it. Okay? Yeah, I'm blocking all the fire exits to protect. All right. So there's another one that I've done. You can also see that that one down the bottom is also linear. It's not separable. It's not separable. Okay? So the final form would be something like that. Okay? Now, if you're a bit cheeky, you can also solve it using the quotient rule. That's the one rule we haven't talked about yet. We've talked about chain rule for derivatives, product rule for derivatives, and people are going, come on, what about the quotient rule? Right? Let's not exclude them. Let's include them. Well, you can actually solve some of these problems using the quotient rule, which is amazing, right? It's amazing. So, okay. Bump. All right. So let's get on to second order problems. And this is mostly what Mobius is about this week. Okay? This is really what Mobius is about. I did notice, I just would feel better if I deleted this. We'll do that later. Okay? Method of undetermined coefficients comes later. So, but think back to Math 1B and these second order derivative type problems. Okay? Some people will be having happy memories. Some people will be like, oh, what a nightmare. Some people are like, I never learnt them, right? I never learnt them. Well, now's the time. Okay? So, notice in the title, we now have not first order problems anymore, second order problems. Okay? Time to wake up. It's almost over, don't worry. It's almost over. If you're sleepy, like there's comfy stuff down there. You can if you want. Okay? So, we're no longer doing first order problems. Now we have first order and second order derivatives in our equation. Okay? So, where do these problems arise? So, A, B, and C are constants. But let me give you an example, right? The main thing for these is something like this, like, I don't know, you've got a spring on a mass, and you've got a spring and a mass, and the mass might be contained in oil, right, or honey or something, okay? So you've got the thing vibrating. You've got a spring on it that wants to sort of return it to where it came from originally. But you've also got some oil which is damping the movement, okay? So in this world, y is the displacement from the initial kind of state. So, it just hangs there without any sort of motion or anything like that. You compress the spring, or you pull the spring and you let it go, and then it moves, right? Okay? So, in this situation, A might be the mass. C could be the spring constant. So, the larger C is, the stiffer the spring. So, the more it wants to sort of return quicker. And B is like a drag coefficient. Okay, that's like got to do with the thickness of the oil. Yeah. So the higher B, the thicker the oil. Okay. It's called Hooke's law. It's like these things are just proportional. proportional to velocity, proportional to displacement. That's where sort of your B and C come in. Okay? So that's an example of where these differential equations arise, yeah? So how do we solve them? How do we solve them? So here are some examples of 3 different problems. Okay? Now, think back to first year. How do we actually solve these things?
Characteristic.
Yeah, the characteristic equation. It's like a polynomial, a quadratic, right? But where does that come from? You're right. We solve some sort of, quadratic equation, but does anybody know where does it come from? Anyone? Because you just get into the mindset, right? Oh, write down the quadratic, solve it, look at the roots, all that sort of stuff. Anybody know? Anyone? Anyone? Okay, it's been a long time, I understand. So, for part A, you have this special equation called the quadratic, which you solve, great. But where does that come from? Well, you can assume the solution is something like this. Okay? It's an exponential. Now, and lambda here is, it could be a real number, it could be a complex number. Okay, you don't know. Let's just keep it open. Okay? So, where does that come from? Well, think about it. Let's look at the first problem, part A. You want a function that doesn't change too much when you differentiate it. Okay, so the double derivative plus 4 times the derivative plus 3 times the original function all has to cancel each other out and give you 0. Okay, so think about a function that doesn't change too much when you differentiate it. Exponential is one. Cosine, sine, they sort of oscillate. But exponential is a good starting point. Okay, so if this is my starting point and I want to find this lambda, it doesn't matter if lambda's real or complex. These are the derivatives. Okay? Yep. So if I take them and I sub them into the equation A, what's going to happen? Okay, well, they're all going to have exponentials in them. Watch what's going to happen. So let's factor out the exponentials. Now, is that square bracket thing looking familiar? Yeah, that's the characteristic equation. This bit can't be 0. So that means that's forcing that to be 0. So that's where the characteristic equation comes from. And it doesn't matter if this lambda's real, complex, who cares? It still works. Okay? So, let's go back. How can we solve this? We can factorize it, hopefully. And then maybe we'll get 2 solutions. Okay? So let's factorize it and see what we can come up with. So the characteristic equation here is going to be this. And if we know lambda, then we know the form of our solution. Okay, so let's factorize it. So multiply to give 3, add to give 4, 3 and 1 will work. Okay, So, lambda is going to be -3 and -1. So our solutions are going to be of the form e to the -3x and e to the -1x. Okay. So the only problem there is there's two of them. There's two solutions. Is that a problem? It seems a bit weird. But did anyone know what can we do with those two solutions?
Was it like you can get any combination of the two and it'd still also be a solution?
Yeah, exactly. So when we talk about linear equations, we're saying if you've got two solutions, you can add those two solutions and the sum or the difference or any combination will also be a solution. So exactly. Exactly. So let's look at the full solution, if you like. Okay? That is the full solution for part A. We don't know what A and B are, they're just constants. Okay? If we had some initial conditions or some extra information, we could determine A and B, but we can't because we're not told what that information is. Okay? All right. So the most important thing, as everybody really knew when I introduced this, is the characteristic equation. Okay? That is, from a computational perspective, it's the most important thing. Okay? You don't need to know the other stuff, but you need to know that equation. Okay? So let's look at part B and see what happens. Let's look at part B and see what happens. Okay? So for part B, notice the coefficients of these derivatives and the coefficients of the characteristic equation are the same. Oh my God. So for part B, the characteristic equation would be 1 lambda squared plus 4 lambda plus 4 equals 0. Okay. Right? So you take your cue from the coefficients 1, 4 and 4. Okay? So now what will that factor to? How do we solve that? What's our lambdas going to be? Well, we want, yeah, so we want to multiply to give 4 and add to give 4, so 2 and 2, so there'll be -2, right? Exactly, thank you. Okay, so, yeah. So in this case, there are 2 of the lambdas, and they're the same. So there's a problem here because I would expect 2 different solutions, not e to the -2x and e to the -2x. So does anyone remember what do we do from Math 1b? Yeah, multiply one of them by x, okay? So the tempting thing is to say, oh, well, it's that. But they're the same thing. So if you add them together, it's not like they're like independent of each other. So as a good rule of thumb, multiply by the x until they're no longer the same. Okay, then you can do a linear combination. Ba-bow. Okay. How are we going at home? Okay, not much happening at home. 17 people are holding on. All right. For the third one, part C, we're going to get complex valued solutions for our characteristic. Okay? So let's just note that. And so it's going to be 1 lambda squared plus 2 lambda plus 5 equals 0. Okay, so there's a very cool technique that I like to use a lot called completing the square. Okay, completing the square. It allows you to solve these things when there's complex solutions pretty easily. Okay, so the way that I do it is I take half that coefficient, square it, and add it and take it away. Okay, essentially you're just breaking up that 5 into 1 squared plus 2 squared, and the first 3 terms are a perfect square. Okay? But you can solve these things any way you like. That's a perfect square, right? All right, take the 2 to the other side, you get negative 2 squared, and so all right? So, assuming you can solve that quadratic and get the complex lambdas, what does the solution look like? Well, you've got an exponential in there, but you've got cosine and sine as well. Okay? So, for this particular example, think back to Math 1A. Yeah. Okay. So the negative 1 goes with the exponential. The 2, positive 2 in this case, goes with the cosine and the sine. Now you can check that they're all solutions by differentiating them and plugging them into, for example, the original equations. Okay? Whew. Now, why would you want to know something like that? You learned it in first year. Why do you need to know it again? Well, we're going to use that information to solve much more difficult problems than you saw in first year. Okay, but believe it or not, it relies in part on this. Okay? Questions? So the characteristic equation is important, right? We're going to do something with this stuff later. And it's Math 1B. Math 1, 2, 3, 1. Yes.
I just wanted to clarify, just like the step from the complex number to the final solution, you just get the your, like, if your complex number is a plus minus like bi, you put a as your exponent, and then you put the b inside the cos and sines.
Yeah. But let's say, so that's a good question. So, you know, this real bit always goes with the exponential, and the imaginary part always goes with it. Now, you could put negatives in there if you wanted to. It wouldn't change it, but, I mean, just keep it simple, right? Other questions? Questions at home? Yeah. So this, who's getting flashbacks from 1231? Anyone? Yeah? Getting flashbacks? It's pretty, like, as you can see, a lot of first year gets repeated in this course, and then sometimes we'll use that stuff to do slightly more difficult problems. Yeah. There we go. It's like the big like lead up.
It's not worth the lead up. Okay, I just had a question about the a cos 2x plus b sine 2x. Is that?
Yeah.
I forgot a lot of first year maths. Is that supposed to be part of the power, or why is it down below?
The power?
Yeah, is it supposed to be part of the, because like all the other solutions, it was like e and then to the minus, like,
Yeah,
so it was part of the power.
exponentials,
Yeah, yeah.
Oh,
So
no.
why is it down?
Yeah. So, I mean, basically in this case, the lambda's complex valued, right? That wasn't the case in the other ones. Yeah. And you can use things from Math 1A like Euler's formula and that sort of stuff to come up with that. So this is just multiplying here with the square bracket. It's not sort of up in the exponential or anything. But yeah, this is the most difficult case, okay, of complex roots or complex lambda. Okay, so yeah, that's one way to write it, and you can justify it using Euler's formula and stuff like that. But it's tricky. I don't really want to do it here, but yeah, that's the hardest one. You could, yeah, you could do that. But we're only really interested in real valued functions, though. Okay, so you know, if you wanted to fight the power, right? You wanted to say, no, I'm going to smash the system, right? And do it's e to the negative 1 plus 2i plus e to the negative 1 minus 2i, all times, you know, x or whatever. You could do that. It may not be super useful format for you though. Like how you get, and we choose the real part. Yeah. Good question. Okay. All right. Okay, so that is basic revision from first year. Okay. So here's the bigger picture. There's 3 cases. Now, even if you didn't learn this last year, it's good to know it now because we're going to use this all the time. We're going to use it all the time to solve much more difficult problems. Okay? So this is really the sort of the... Without this, you won't be able to solve anything else. That's the problem. Okay? More questions? Okay. All right. So, yeah. Okay. Yep. So these ones are pretty, you know, pretty simple, and you can see from the solutions, oh well, the roots are real and unequal in the first case. They're repeated roots in the second case. And in the third case, it's obviously complex roots, fully characteristic. Okay? All right. Oh, hello, welcome. Are you waiting for the next class? Yeah. Okay, so you can stay on one condition. Just pretend like you're paying attention. Is it okay? Is it right? And don't talk. And no headphones. Okay? It's very comfy out there. I don't actually know why people come inside because it's much comfier out there. All right, other questions? It's pretty easy, okay? It gets a little bit more difficult if we move to a problem like this. let's say we have, okay, I think I showed this to you before. Yeah. Okay, here's our spring mass system again. Yep. So here's our spring mass system. So we've got a mass on a spring, and we perturb it, we give it a push or a pull, and we let it go. Okay? And so what's acting on that? Well, the spring is acting on that, the oil is acting on that, right? Gravity is acting on that, all sorts of stuff. What happens if I tap the mass? Right? So I pull it, I let it go, or I compress it and I let it go, and then I'm constantly giving it a nudge, or I'm giving it some sort of force to keep it going, or not let it get to rest. Okay? In that case, the right-hand side is no longer zero. Okay? So it's like an external force. Okay? The force might be a wind or something else. Okay? So how does that affect the system? Okay? And it affects it a lot, and it's something that we can also potentially control. Okay? So that's the sort of the next piece of the puzzle, right? We're thinking about no external force, what happens? Well, characteristic equation, blah, 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 blah. And then the next step is what happens if you have a vibrating system and you give it a tap or a nudge or something. Okay? And it's quite interesting because it can change the dynamics of the system a lot. All right? So let's just think about it for a second. What happens without the external force? Well, the thing will just go up and down, and it'll probably come to rest at some point, right? But if you keep it going, let's say you absolutely smash it, right? You absolutely smash it. What's going to happen? Well, your system's going to maybe vibrate apart. You might get something called resonance, whereas small vibrations get bigger, right? And eventually the system just disintegrates. These are all possibilities. So that is our next port of call. Yes. Okay. The non-homogeneous or non-homogeneous. Non-homogeneous. Yeah. Non-homogeneous. Okay. So again, these were, if you look at the bottom three equations, these were in Math 1, 2, 3, 1, yeah? So if you can do the first stuff, then this stuff isn't too bad. Okay? It isn't too bad. So, can anyone remember, how do you solve these problems? How do you solve part A? Oh, you make me getting up now. I was a bit tired.
I mean, this is me vaguely remembering, but like you do it in like the homogeneous way while it's zero, and then you like plug back in, and then you work it backwards or something.
Yeah.
Yeah.
So the first thing is you imagine this is zero and you solve that case. And then you say, oh, let's find a second sort of extra bit and we'll fit it to that equation. Yeah? Okay, that's perfect.
You want it back, the mic?
No,
I can walk there.
no, can you?
Yes.
Come on down.
All right.
Yeah. This is good. Come on, give me a hand. Come over. Yes. All right. So that's exactly right. Okay. So based on this form, you make a guess. And the guess in this case has the same form as whatever the function is. So for part A, you would solve the homogeneous problem, and then you would make a guess at the form. But why does it work? And let me show you a way to solve these problems super quick that you wouldn't have seen in first year. Okay, I probably shouldn't be telling you this, but you know. Watch this. I don't want to solve that. It's too hard. Let's differentiate both sides of the equation twice. Differentiate both sides of part A twice. What's going to happen to 2x plus 3? It's annihilated to 0. So what have we got? We've got a homogeneous problem now. Oh, yeah. Okay, so let's differentiate both sides twice. Okay? Now, this is a fourth order problem, but we kind of know how to solve it. The important thing is it's homogeneous. So what is the characteristic equation for this? It's going to be lambda to the power 4 minus 5 lambda cubed plus 6 lambda squared. Am I right? Okay? So how can we solve this? Well, luckily there's a common factor of lambda squared. Yeah? There's a common factor of lambda squared. And I can factor that bracket. What have I factored it to? Oh yeah. Negative 3 and negative 2, yeah. Okay, so what is my solution to the characteristic equation? It's 2 and 3 and 0 and 0. Okay? 2, 3, 0, 0. All right? So let's write that down. Okay, what was that? Question? Oh! I was getting so excited. Thank you. So, what are our solutions going to look like? They're going to be exponentials.
Sorry, the question before we get to that.
Oh.
Why are we dipping it twice instead of just once in terms of y? Because then the 2x just gets the others.
Well, the 2x will be 2.
But if you different in terms of y.
No, I'm not differentiating in terms of y. Because y double dash here is d squared y dx squared. Yeah. So, okay. So what are our solutions going to be? Well, e to the 2x, e to the 3x, and then what do we do with these? Well, e to the 0x, what's that? That's just 1. And we've got another e to the 0x. Yeah. So, we're going to have all right, we're going to take that one and multiply 1 by x. So, 4 solutions. Linear combination of 4 solutions. Okay? Linear combination of 4 solutions. Okay, let's do c times x and d times 1. Okay, all right, now, once you've got that written down or in your head or whatever, watch this. Watch this. Can you see how this extra bit is the same form as that? Oh my God. All the lies they told you in first year, everything they hid from you is now open, right? Hang on.
In regards to the earlier question, I'm just clarifying if we're differentiating the left-hand side with respect to y and the right-hand side with respect to x.
No. So we're just differentiating this with respect to... So this is. Okay, so we differentiate that with respect to yeah. So we're differentiating that with respect to x, that with respect to x, and that'll become 0, right, if we do it twice.
Yeah, and is this a formal method?
Not in first year. It's a real method.
Okay, perfect.
Yeah, I'm not just making it up. Yeah, it's a real method.
Can I share this forbidden knowledge with the first years?
You can, yeah, if you want to. You can. Sometimes it's useful, sometimes it's not. So, but it's useful enough to know. Oh, okay. Yeah. Oh, yeah. Oh. Hang on. No, because there's no initial conditions. We don't have any data for part A, right? Any extra? Yeah, we just don't. We don't know what it is. Yeah. Yeah. Hang on. Yeah, you take that one. Oh.
Why did you circle the cx plus d and
okay,
the 2x plus
so
3?
what have I circled in that picture? Cx plus d, 2x plus 3.
So cx plus d is 2x plus 3.
No, it's just the same form.
Okay.
So we don't know what cx and d are, but this extra bit, that's a linear equation or linear function, right? It's a line.
So that's like the second part that we could find with the particular solution.
Yes.
Okay.
That's where it comes from.
Okay.
That's where it comes from. Okay? Yeah. So now you know, people. Now you know. You know where it comes from. And you don't have to guess so much. Okay? You don't have to guess so much. Okay. But it's not always possible to do this. Let me show you. Look at part B. Okay? Part B. So if I was to copy that method to part B, how can I get rid of? How can I annihilate this thing? By differentiating it. Can I do it in the same way that I did it in part A? Because if I differentiate it, what do I get? 60 e to the 5x. And then if I differentiate it again, I'm going to get 300 e to the 5x. I differentiate it again, I'm going to get 1500 e to the 5. It seems like it's getting more complicated, right? Right? Oh, different. Yeah, just keep differentiating. Yeah, it's like matrices. You just row reduce everything. Just keep going. Aha! But what happens if I differentiated that and then took away 60 times that? Oh. It's possible, but it's harder. Okay? So I wouldn't recommend it. Unless it's super easy to do, I wouldn't recommend it. Okay? So what do we do with this one? What do we do? Well, let's go back to first year. The characteristic equation is so lambda squared minus 5 lambda plus 6. You can factor that, of course. You get the same thing as up here. So the so-called homogeneous solution or homogeneous solution. Okay? That's like half of the solution to the original problem. The second part is assuming there's an extra bit that is of the same form as the right-hand side. Okay? So to do that, let's assume our extra bit is c times e to the 5x. Okay? C times e to the 5x. So the y sub p, the p means particular, a particular solution. Okay, c is a constant here. We don't know what it is, but we want to find it. Okay, We don't know what it is, but we want to find it. Okay? So, let's compute the derivative and plug everything into my original equation. Okay, so with those three things, we'll go up to my original problem, plug in there, there, and there, and set everything equal to 12e to the 5x. All right, so we've got 25 there. And we're going to get 25 here as well. And here I'm going to get 6c. All right, so cancel, cancel. 6c is going to be 12, so c is going to be 2. Okay? So, we take our original equation and we're going to say, right, we're going to add that to that with c equals 2. Okay. Great. Okay. Questions? It's a little bit time consuming. It's not as nice as the previous solution. But by the way, you mentioned C and D in the previous solution. You could find them, by the way, if you wanted to. I think I said the wrong thing before. Okay. But it's you sort of got to guess based on the form. So over here, that right-hand side formed the basis of our guess for our extra bit, our particular solution. Questions? Comments? Observations? Criticisms?